Welcome back, everybody. In this video, we're continuing with section 3.6 on working on finding zeros of polynomial functions. And where we'll start here is by looking at something called Descartes' rule of signs. And what Descartes' rule of signs is about is it gives us a way to tell approximately how many positive zeros a polynomial may have, how many negative zeros, and then how many complex zeros. So let's see how this works. So the statement of Descartes' rule of signs is up here. It says if we have a polynomial function, again, highest degree term is a and x to the n, and it goes down to a1x, a0. And it has to have real coefficients for this. Okay, and then there's two statements here in bullets. Okay, it says the number of positive real zeros is either equal to the number of sign changes of f of x or is less than that by an even integer. Or the number of negative real zeros is either equal to the number of sign changes of f of minus x or is less than the number of sign changes by an even integer. By sign changes, you also hear that it's described as variations in sign. So I need to tell you about what is meant by that first, and then we'll see how to actually apply that to Descartes' rule of signs. All right, so here we'll take this first polynomial on the left. P of x is x cubed minus 2x squared minus 5x plus 7. And so we want to think about how many variations in sign that has. And that doesn't have to do with what the graph looks like. That literally has to do with the formula. So this starts off with positive x cubed, but then it switches to negative 2x squared. So it switches from a positive to a negative coefficient there. So that's one variation in sign. Then from negative 2x squared to negative 5x, still negative. From negative 5x to positive 7, that's switching from negative to positive. So there are two variations in sign. Okay, let's try that again. For f of x here, it's positive 1, positive 1, positive 5, and then positive 1. There's no variations in sign. Okay. For g of x, it starts off as 1x squared, so switches then to negative 4. So that's one sign change, and then it stays negative. So there's only one variation. When you're counting variations in sign, what you're doing is just scanning the formula for the function left to right and counting whether or not the sign on the coefficient changes or not in moving from one to the next. Each time there is a change, you want to count that, accumulate that. All right, so now I've restated what Descartes' rule of signs here says. There's basically two statements. One tells about how many positive zeros there are. The other one tells about how many negative zeros there are. Let's take positive first. The number of positive zeros is either equal to that number of variations or is less than that by an even whole number. So for this example we did up here, where it said two variations in sign, that would mean that there are either 2 or 0 positive zeros. For the second one, where there were 0 variations in sign, that means we know that there are no real zeros for that polynomial. Okay. For the last one, there was one variation in sign, so you're guaranteed to have one real zero there. Okay. All right, for the negative statement, you basically do the same calculating how many variations in sign there are, but it's of p of minus x. So you replace x by minus x and count variations in sign on that. I'll show you an example. Okay, so here we're going to describe the zeros of each of these polynomials. So let me first count the variations in sign on this f of x that's on the left. So it goes negative, still negative, now positive, now negative, and stays negative. So there are two variations in sign. That means that there will be 0 or 2 positive zeros. Okay, now we want f of minus x. Okay, that will be plus 21x to the 5th minus 3x to the fourth minus 2x cubed plus x minus 4. Okay, here I've replaced x by minus x and simplified a little bit, okay? Positive 21 to negative 3, okay? Stays negative, back to positive, and then back to negative. So here there are 3 variations in sign. So that means that there will be 3 or 1 negative zeros. Okay, so you count the variations in f of minus x to tell about the number of negative zeros. It's either equal to how many variations in sign you have, or is less than that by an even number. So basically count down by 2's. 3 minus 2 is 1, and then from there you can't count down by 2 without going negative. So it's just either 3 or 1. Okay, so then what's possible? Is listed there. So here this doesn't take into account, we haven't described how many complex zeros there are. So there's several possibilities there. We could take a look at that in just a minute, but I wanted to do one more where we just count real zeros first. So for this g of x, it's first positive to negative, then negative back to positive, then positive back to negative. So this has 3 variations in sign. So that means that you will have 3 or 1 positive 0. So you get at least 1, but you could have 3. You won't have 2 though. Okay, it'll be either 1 or 3 positive zeros. Okay, now we want g of minus x. Okay, g of minus x will be negative x cubed minus 4x squared minus 2x minus 3. This one, all the coefficients are negative, so there are no negative zeros. Okay, so then here we can think about what's possible, right? The degree on this thing is 3, so that means there has to be 3 zeros altogether. So we could say how many positive, how many negative, and how many complex. We haven't seen examples with complex zeros yet. We will soon. So we saw that there were no negatives, so we could have either 3 or 1 positive zeros. There will be no negatives. We know the degree on this thing is 3, so there's a total of 3 zeros. So we could have 3 positive, no negative, and no complex. Or we could have 1 positive, no negative, and 2 complex. So those are all of our possibilities. For the preceding one that we did, we saw that that has degree 5, so there will be 5 zeros. Here there's a bunch of different possibilities. For positive zeros, it could be either 0 or 2. For negative zeros, 3 or 1. So if we want to try to think about what's possible incorporating complex zeros, maybe we can make like a tree diagram for this. So the number of positive zeros is either 0 or 2. Okay, and then the number of negatives is either 3 or 1. Okay, so I'm just trying to go through all the possibilities. There could be no positives or 2 positives. There could be 3 negatives or 1 negative in each case. For complex, let's see, we have to get to a total of 5 zeros. If there were no positives and 3 negatives, there would have to be 2 complex. If there were no positives and 1 negatives, there would have to be 4 complex. If there were 2 positives and 3 negatives, there would have to be no complex. If there were 2 positives and 1 negative, there would have to be 4 complex. Sorry, that's 2 complex. The total has to always equal 5 zeros. Okay, let's see that happen again. Okay, so here in this example, it says use Descartes' rule of signs to determine how many positive and negative real zeros this polynomial may have. Notice the degree on this thing is 3, so we should expect a total of 3 zeros. So we have our p of x, which is 2x cubed minus x squared plus 4x minus 7. So it switches from positive to negative, negative to positive, and then positive back to negative again. There are 3 variations in sign. And so there will be 0, no, 3 or 1 positive zeros. Okay, and then let's take a look at p of minus x. That will be negative 2x cubed minus x squared minus 4x minus 7. This one, there are no variations in sign, so there will be no negative zeros. Okay, so to summarize that, if we know that there is no negatives and there are 3 total because the degree is 3, we could have 3 positive zeros, or we could have 1 positive and 2 complex. Okay, how Descartes' rule of signs benefits you is we saw that with the rational zeros theorem, that gives us a whole bunch of different, potentially a whole bunch of different possibilities for what the zeros may be. If we can go through looking at like Descartes' rule of signs and find out, for example, that there's no negative zeros, then that could potentially really decrease how many rational zeros we might have to test. Okay, we'll have an example in which we do that coming up shortly. All right, so let's take a look and see what we have here. Okay, so we have this polynomial. We want to figure out how many rational zeros or what rational zeros are possible. We'll see what kind of information we get out of Descartes' rule of signs, and then we'll go from there. Okay, so the possible rational zeros will be factors of 4 first on the top, plus or minus 1, 2, or 4. In the numerator, denominator will be factors of the coefficient of the leading term. That's 1, luckily for you. So it's just negative 1 and 1, negative 2 and 2, and negative 4 and 4. So there are 6 possible rational zeros. There may be some irrational zeros, I don't know. But there are 6 possible rational zeros. Let's see what Descartes' rule of signs gives us. Taking a look at the initial polynomial, there's no variations in sign in the original f of x. So that means that there is no positive zeros. Okay, so how that helps is that means that now we don't have to check and see if 1, 2, or 4 is a 0. It might be negative 1, negative 2, or negative 4. We'll see. Let's find f of minus x next. Okay, f of minus x will be negative x cubed plus x squared minus x plus 4. That has 1, 2, 3 variations in sign. So there will be 3 variations. So there will be either 3 or 1 negative 0. Okay, if there's 1 negative, then that would mean that 2 would have to be complex. So what's possible at this point is we could have no positives, 3 negatives, and no complex, no positives, 1 negative, and 2 complex. All right, so that will be our possibilities. As far as checking to see if any of these are zeros, we could do trial division to check. We know, though, at this point, all we have to check, though, is the negative ones. So let's start working on that. Let's do that up here. I'm going to start with negative 1 and just kind of go in order, okay? So negative 1, we want to see if that's a 0. It's 1x cubed, 1x squared, 1x, and a 4. Okay, so we're going to repeatedly multiply and add, and then hopefully we will get to where we have a 0 remainder, which will tell us we've got a 0. Okay, so negative 1 times 1 is negative 1. Here we're adding, getting 0. Negative 1 times 0 is 0. Adding will get 1, and then this gives us not 0. So it's not -1. Let's try -2. Okay, you can check this by substituting these values into f if you want, but considering our goal is to eventually find all the zeros, I think it's just easier to use division. Okay, so -2 times 1 is -2. 1 plus -2 is -1. -2 times -1 is +2. 1 plus 2 is 3. -2 times 3 is -6. And then that will again add up to -2, which is not 0. So it's not -2 either. Let's try -4. Okay. Okay, so -4 times 1 is -4. -4 plus 1 is -3. -4 times -3 is +12. And that looks like it's getting far away already. So we've got 13, we'll have -52, -48. All right, so it doesn't look like we have rational zeros for this one. So that's it. For this one, we've exhausted all the possibilities for rational zeros. All right, so in our next example here, we're going to actually try to find all the zeros. Our polynomial has degree 4, so we should end up with 4 zeros. That's a lot. And so we're going to start by examining what the possible rational zeros are. And then we'll see about using Descartes' rule of signs to narrow down our search a little bit. Okay, so the possible rational zeros are going to look like fractions. Their numerators will be factors of 4. So we have plus or minus 1, 2, and 4. Those are all the factors of 4, our constant term. And then we'll have as denominators factors of 2, which is plus or minus 1, plus or minus 2. All right, so we want to write out all of our zeros. I'm going to first write down all the ones that have a denominator of 1. So that'll be -4, -2, -1. And then we'll have positive 4, 2, and 1. Okay, that's all the ones with a denominator of 1. Now let me do all the ones with a denominator of 2. So that will be plus and minus 1/2. So -1/2 and +1/2. Then 2 over 2. 2 over 2 is just equal to 1, and I've already got that, so we'll skip that. And then 4 over 2 is going to be 2, and we actually already have that. So there's all of our possible rational zeros. Let's see what Descartes' rule of signs can tell us. So the number of variations in the sign for f of x. So it's plus, it's pluses all the way down. So that means that there's no variations in sign, and so there's no positive zeros. Okay, and how that's great is that means that all these rational zeros that are positive, we don't have to check any of them. Okay, so that cut down our search by half just a little bit. Okay, so now let's check for f of minus x. So f of minus x will be 2x to the 4th power minus 15x cubed plus 31x squared minus 20x plus 4. So that's long, so we'll go plus to minus, minus to plus, plus back to minus, and then minus back to plus again. So this one, that's kind of the worst possible news in a way. There was 4 variations in sign, so we could have 4, 2, or 0 negative zeros. Okay, so that really doesn't help us at all, right? So I guess that means we were not going to end up with 3 negative zeros. It's going to be 0, 2, or 4. So as far as trying to find them, we're going to, again, just kind of do trial division to see which one of these may fit, and hopefully at least one will work. And so I'm going to start with -1 just because 1's easy to work with. And we're just going to divide for each one. So we'll have -1. I've got 2x to the 4th power. 15x cubed, 31x squared, 20x's, and a 4. Okay, and then the 2 drops straight down. So we're going to divide. We're going to hope to get a remainder of 0 here. So this gives us a negative 2. There's 13, negative 13, and then 31 minus 13. That is going to be 18. Yeah. So negative 18, 2, and no, right? It's not going to work at this point. So negative 1 didn't turn out to be 0. Let me try negative 2 next. Okay, so we'll have negative 4, there's 11, there's negative 22. 31 minus 22 is 9. Negative 2 times 9 is negative 18. That's looking a little better. We've got 2. Yeah, we finally got one. Okay, so one of our zeros turned out to be negative 2. So, and we've also got a partial factorization of our f of x. So now f of x is looking like x plus 2. We know negative 2 is a 0, so x plus 2 is a factor. And then that quotient is going to be 2x cubed plus 11x squared plus 9x plus 2. All right, so in working with the smaller piece, you can try with the rational zeros test again, but you're not going to get new zeros that you didn't already have. Okay, so I don't need to check positive anymore because it's going to be the same. And we've already found that negative 1 wasn't a 0, so it's still not going to be a 0. Negative 2 could be a 0 again, and negative 4 could still be a 0. So we're going to try negative 2 again on this smaller part. So we'll try negative 2 again. So that will be on 2x cubed, 11x squared, 9x, and 2. The 2 will come down, so we're dividing again. So negative 2 times 2 is negative 4. 11 minus 4 is 7. Negative 2 times 7 is negative 14. There's 5. No, that was a 14 negative. So negative 5. And positive 10, so that's not a 0. And so then we'll try negative 4 next. Okay, we'll try this one. Hopefully this will work out. Negative 4 times 2 is negative 8. 11 minus 8 is 3. Negative 4 times 3 is negative 12. 9 minus 12 is negative 3. And then negative 4 times negative 3 is positive 12. And so that gives us 14. So that one also not a going to be a negative 0. All right, so then going from here, we'll have to see what it is that we can do next. All right, so we've seen that negative 2 no longer is 0 and the negative 4 isn't. We haven't checked negative 1/2 though, so let's check negative 1/2 next. And that will be basically our last hope. Okay, negative 1/2 times 2 is negative 1. 11 plus negative 1 is 10. Negative 1/2 times 10 is negative 5. 9 plus negative 5 is 4. Negative 1/2 of 4 is negative 2. And finally, that one will give us a 0 at long last. So now we've found that one more 0 is going to be negative 1/2. So we have x plus a half as a factor. And then what's left will be 2x squared plus 10x plus 2. Okay, as our partial factorization. And then I'm going to factor out a common factor of 2 from this quadratic and distribute it into the second of the binomials. So this will be x plus 2, 2x plus 1, x squared plus 5x plus 1. All right, and the reason for doing that is, for one, to make it so that we have just the integer here instead of having a half, and then also to lower the coefficients on that trinomial that we have. All right, so this has taken so long, we forgot the directions, or I forgot the directions. We want to find all the zeros. Okay, we've gotten 2 of them. I need to get 2 more. They're the zeros of x squared plus 5x plus 1. And so you can use quadratic formula or completing the square if you want to get this done. I'm just going to use the quadratic formula because people typically like that. So we'll have quadratic formula. Okay, so a little simplifying the radical. All right, so the other 2 zeros will be -5 plus or minus square root 21 over 2. So those were irrational zeros. Remember that the rational zeros theorem doesn't tell us anything about those. So let's see what we've got. So that's -5 minus root 21 over 2, -5 plus root 21 over 2. And then we saw that we had -2 and -1/2. So there's our 4 zeros for this one. I'm going to go ahead and add in the decimal approximations on those two, just so you get a better feel for how big those are. All right, so it turned out that we ended up with 4 negative zeros from doing this. All right, so in looking back, you can tell that this wasn't a quick problem, that's for sure. If we had seen maybe earlier on one of the other zeros, we might have taken out some of this trial and error that we needed to do. We saw that using Descartes' rule of signs, that made it at least so that we didn't have to try and check the positive zeros. But we finally got it, and so that's good. We haven't finished yet section 3.6. We'll keep working on it, but that does take us to the end of this video. So let me know if you have any questions, and have a great day.